It says the distribution of amount of time it takes Chris to get to work on the bus is shown in the dot plot. We've got a whole bunch of different times, commute times here. There are so many dots packed on there, they're like overlapping and almost impossible to count. But we're supposed to figure out on about what percent of days does it take between 8 and 11 minutes for Chris to get to work. So I'm going to just kind of mark off my area of interest, 8 to 11 minutes. Let's think back to the last chapter and something that some of you struggled on in the last test, which is describing a shape of a distribution. If this is a dot plot, what shape would this distribution be really closely aligned to? Not symmetric, actually. Yeah, that one. Very good. Uniform. That one, she said, and put her hand in the air. Okay. Symmetry would mean that it's not straight across. It's got some symmetry to it, which could be bell-shaped. It could be a dip in the middle. It's got symmetry, but it's not straight across. Well, this one, these are so packed closely together into almost a rectangular shape that we're going to use that to our advantage, okay? Now, I don't have to actually count the dots in my area of interest and put that over the entire amount of dots because I can't count them. I'm going to go ahead and say that's impossible. But I can use these numbers on the axis to help me. The lowest commute time for Chris appears to be 5 minutes, and the highest appears to be 13 minutes. So, what's the range there? 8 minutes. But my area of interest is from 8 to 11 minutes, and what range does that have? So I'm going to use the numbers on the axis to my advantage, and I'm going to say 3 out of 8 will give me a really good idea of the percentage of days, of the percentage of dots that are in this region here. And if I grab my calculator and I do 3 divided by 8, I get 0.375. You always look back and say, did they want me to give it in the percent or proportion? If it said proportion, then I'd be done. I would just write a sentence. But it said percent. So on about 37.5% of the days, it takes Chris between 8 and 11 minutes. You could put to commute to work, to get to work, but be as specific as possible and be sure you write it in context if this was a free response question. Now obviously that's not a normal bell-shaped curve. We'll get into that in just a second. But in general, what is a density curve? Believe it or not, we used a density curve. That straight line that I drew across the top there is considered a curve. It's a type of distribution. A density curve, let's just keep it to the really important stuff. The area underneath any density curve is one whole. One whole representing 100%. I'm talking about skewed left, skewed right, uniform, bell shape. Any density curve has an area underneath of 1. That's really important. Okay, well, why would we use these? And we use them, they are used to approximate, kind of like we did at the top of the page, we approximated. They're used to approximate distributions, specifically of quantitative data, numeric data. So like if I had a dot plot and it looked pretty bell-shaped, then I could use a density curve, which happens to be a bell-shaped or normal density curve, to approximate that data. So the curve itself is an approximation. That's why they're valuable to us, so that we don't have to be exact. I'm going to go pretty quickly through this next part because we've already touched on this in this class. How would you identify the location of the mean and median for any density curve? Whether it's left skewed, right skewed, or symmetric, the mean is the balancing point. That's a good way to estimate where the mean is. And I've got that illustrated for you over here with this little triangle. Think of it as a teeter-totter. This density curve happens to be extremely skewed right. So the bulk of it is over here. So if I had to balance this on a teeter-totter, I would balance it right about here. So that's where I would approximate the mean would be located. However, the median, that is simply going to just cut the area right in half. So it's the equal areas point. Over here, I'm going to say the median would be somewhere right there. How did I know the median was to the left of the mean in this right skewed distribution? Think of old knowledge that you have. Because it's right skewed, but be more specific. But you haven't told me why. Does somebody over there have an idea? Ooh, yeah. Do you remember how we talked about the mean gets pulled in the direction of the tail? Because the mean is great, but it's not a resistant measure of center. So in any skewness, we want to avoid describing the mean, and we choose median because it is resistant. So if you forgot, in a right skewed distribution, the median is always smaller than the mean. And the opposite is true for right skewed. And in symmetric, they're the same. All right. Can you identify the standard deviation? Not unless you know calculus. You would not be able to tell me an approximation of standard deviation unless ... you've got a normal density curve. What is a normal density curve? It's a specific type of density curve that is symmetric, bell-shaped, and unimodal. It's where we're headed in statistics. It's the classic statistics bell-shaped curve. So let's just draw it really quickly. You are going to draw a ton of these today. So it might feel awkward at first to get this symmetric shape, but do the best that you can. And I want to make sure you're comfortable with symbols. So smack dab in the middle, we're always going to say that that's mu. That is the mean. And so I told you a second ago, if you have skewness, then you would need calculus to figure out the standard deviation. The beautiful thing about normal curves is you can tell me approximately what the standard deviation is. If I had a number line down here and I had you estimate, I'm asking you really, how far out do I draw that first tick mark? How do I know it goes there? Okay? And the reason is because we're looking for something called the point of inflection. And you might want to hear my definition before you draw it on your paper. And you can kind of see this has an S shape to it. The second that it goes from concave or convex to concave, as soon as it switches direction, that's your point of inflection, and usually right underneath that is where you can estimate that first tick mark to be. And it just kind of depends on how you drew your picture. But we always go 3 standard deviations to the left and 3 standard deviations to the right, so you might as well get used to it now. And you can show yourself in your picture that from the mean out to that first tick mark, that is the standard deviation. And all the tick marks are 1 standard deviation away from the next one. They're equidistant. See if you can draw the picture that goes with this problem. It's not really a problem, it just wants you to draw and label. According to the CDC, the heights of 12-year-old males are approximately normally distributed. That tells me there's no skewness. The mean is 149 centimeters. The standard deviation is 9 centimeters. I want you to see if you can draw a picture that would be good enough for the AP exam. Give it a shot. I mean, these poor graders, they're going to have to be able to read your handwriting. They're looking for neatness. If you're at the very last test they grade for the day, they're going to be exhausted and angry. Figure out what numbers go on this axis. How are you doing that? Adding 9, adding 9, adding 9, and feel free to write on a slant to keep everything nice and neat and easy to read, especially for 3-digit numbers. Ugh. How do I go to the left? Subtract 9, subtract 9, subtract 9. A million trillion of our problems today involve this specific distribution of heights of 12-year-old boys, so get used to drawing this with those exact numbers down there. Very good, except I'm missing something pretty critical on my graph. These are the points 1, 2, and 3 standard deviations away. I've got that. What would you need on any graph that you draw for the AP exam? You need to label it, you need to title that axis. What are we showing? Well, we're showing the distribution of heights of 12-year-old males, specifically in centimeters. Unless you want to put centimeters next to every single number in the title, you can specify. This is in centimeters. Now that looks fantastic. I'm probably not going to title any of the other ones in the notes just to save a little time, but I've covered it. You need to have it titled. I'll be looking for that, and I grade your next free response, okay? All right, so let's turn the page and talk about something called the empirical rule, and I'm going to show you what it is, why it's useful, when you might need it, and how we can kind of get around using it if we have to or want to. So I actually want to skip down here to what is the empirical rule. When does it apply? You can use this for any normal distribution. And you'll see the word normal capitalized a lot because some people consider it a proper noun because it's a type of distribution. You can use the empirical rule for any normal distribution. So if your problem says you're dealing with a normal distribution, you can use the empirical rule, but it can't be used for skewed, so it can only be used for normal distributions. Period. What is it? There are 3 bullet points. So make sure you give yourself enough room. 1, 2, 3 parts to this. The first one is about 68% of values are within 1 standard deviation of the mean. About 68% of values. That's that blue region that he showed you on the video. 1 standard deviation to the left, 1 to the right, shading it in, 68%. Here is that same information in mathematical symbols. Mu plus or minus sigma. That's the average minus a standard deviation. The average plus a standard deviation. 68% of the data values are between there. The next part is about 95% of values are within 2 standard deviations of the mean. That's mu plus or minus 2 sigma. Does anybody remember what the third percentage is? 99.7. Of values are within 3 standard deviations of the mean, mu plus or minus 3 sigma. The empirical rule can be your friend. Don't think of it as an extra thing that we learned and it loses its value to you once you learn stuff on the calculator. It's a really good tool to estimate some things. You actually might be asked to justify or assess normality, which is what I'm going to show you now. On this problem up here, what we're going to do is we're going to assess normality. We're going to prove whether we think this distribution of test scores is normally shaped or not. I'm thinking that it's got a pretty normal shape to it. If I use a density curve to kind of like estimate that dot plot, it feels like it's normal. Most. But I can prove it. I can figure out the percentage of dots within 1 standard deviation of the mean, and it should be somewhere close to 68%. You are given information up here that's really important. Here's the scores for 50 students on the test. The mean is 76.4 and standard deviation is 7.9. What percent of values are within 1, 2, and 3 standard deviations of the mean? Okay, let's kind of figure out what we're going to do. I need to know the actual numeric values for within 1 standard deviation of the mean. Like, what test scores am I sandwiched between? So grab your calculator and do 76.4 minus the standard deviation. That's the lower end of my boundary. And then 76.4 plus a standard deviation tells me the upper end of my boundary. So I'm looking up here, 68.5 all the way up to 84.3. If you count all of those little dots, you're going to find that 33 out of the 50 are in that region right there. And 33 out of 50 happens to be exactly 66%. Is that pretty close to 68%? Okay, so far so good. Again, what I'm doing is I'm proving mathematically whether I think this should get a normal distribution assigned to it or not. Okay, now I need to see what percentage of the values are within 2 standard deviations of the mean. So 76.4 minus 2 times 7.9. And I like to be efficient with my time, so I'm just going to copy and paste that down and swap out the minus sign for a plus sign, and then I can move right along. So now I'm sandwiched between 60.6 and 92.2. 60.6 and 92.2, and if you count all of those dots, there are 48 of them. 48 out of 50 is exactly 96%. Is that pretty close to 95%? Heck yeah, it is. Lastly, I need to figure out what values are within 3 standard deviations of the mean, and to save some time, I'll go ahead and tell you those are 52.7 all the way up to a test grade of 100.1, and it turns out every single dot, or 100% of the dots, are within 3 standard deviations of the mean. That's really close to 99.7. So what we just did is called assessing normality. It can help us prove whether or not the distribution we're looking at is normal or not. Because sometimes you have to prove it to be able to use normal calculations, which is what the rest of the lesson is about. let's see how the empirical rule can be helpful. Jump down here to where it says, using the earlier example, and this is the one about 12-year-old boys' heights. What percentage of 12-year-old boys will be taller than or greater than 158 centimeters tall? You don't have a ton of room, but we're going to draw a picture, so leave room for your numbers below this axis. Draw a normal curve. And if you've already forgotten from the first page, the average, the mean, is 149. And it goes up to 158, 167, and 176. And it goes backwards to 140, 131, and 122. We want a title on that. Well, it's asking me what percentage would be taller than 158. Well, 158 is right here, so draw a boundary line and tell me which way you would shade. Where are all of the boys taller than that? To the left or to the right? To the left are boys taller than that? No, to the right. Okay. So I just usually use stripes. So striped it in. Well, the empirical rule is all we know right now. Later, you're going to learn some cool calculator stuff, and you may forget about the empirical rule. But right now, that's all we have. So how can I use this information, these percentages, about 1, 2, and 3 standard deviations, to figure out the shaded region right here? Okay, how many of you followed it? Okay. Some of us can't hear him. Okay, what he's saying is this. Within one standard deviation of the mean, the empirical rule says about 68% is within there. But the fact that this is symmetrical is helpful, because what we'll do is we'll assume all of that under there is 100%, and I can just take out the 68%. Well, what's 100 minus 68? 32%. And a lot of students just say, okay, then that's 32%. But what Arian was saying is it's got some symmetry, kind of like the box and whisker plot. But over here, that's included in the 32%. Both tails are included. And I only care about the tail on the right. So what do I need to do with that 32%? Yeah, split it in half. So let's write the work really quickly. We took 100%, all the area under the curve, and we subtracted out that middle 68%. I covered it up with my finger. And that was an easy way for me to tell what I have left over then is 32%. But that's the unshaded and the striped part, and I only care about the striped part, so I'm going to split that in half. So the sentence that would go with this is, about, because again, these are approximations, about 16% of 12-year-old boys will be taller than 158 centimeters. It's not super mind-blowing stuff yet, okay? So let's use the same concepts, and this, I lose a lot of people on this one, so see if you can follow me here. 149, 158, 167, 176, 140, 131, 122. This one says what percentage of boys will be between 131 and 140. We have two regions that are overlapping here. So I'm going to do my best to illustrate this, okay? What I have is I have the percentage of boys that are shorter than 140 centimeters, that's 140 down, and then I have boys that are shorter than 131, so I'm going to cross-hatch it the other way so you can see the difference. So if I can do this, if I can figure out the striped region, and subtract off the cross-hatched region, then I'll have my answer remaining. So if I take all the boys less than 140, and I subtract off all the boys left less than 131, then I'll have a little slice of interest there. I'm going to use this up here, the work that I already did, to help me out. What percentage of boys are shorter than 140? 16%, because it's the same as the 16% over here. So we've already done that work, we don't need to do it again. The same way we found that 16%, we're going to find the cross-hatched area. Any ideas? Not divide by 2, we're not there yet. How do I find just the percentage of boys shorter than 131? It's 2 standard deviations away from the mean. So what percentage is within 2 standard deviations of the mean? So do you remember how I subtracted out the 68 right here? Now I'm just going to subtract out 95. That's all. So I'm going to take 100%. I'm going to subtract out 95. And then I'm going to cut it in half because I only care about the left tail, not the right tail. And you'll end up with 2.5% in that cross-hatched area. I'm taking out the middle 95%, which will leave me with the left and right tail, and then I'm cutting it in half because I only care about the left. 2.5%. If you subtract those, you'll see that about 13.5% of 12-year-old boys are between 131 and 140 centimeters. Is there? So you can take 95% minus 68% and you get 27%. And then cut it in half because you only want one side and you get that 13.5%. That's great insight. That's wonderful. If I lost you on this one, good news. I'm going to show you different ways to do these here in just a second. So if you're like, oh my God, I have no idea what's going on. It's okay, I promise. But I want to take a break from these 12-year-old boys, and I want us to read this next one and see if we can figure it out. It's kind of like a logic puzzle. I like these. It says, suppose that a distribution of test scores is approximately normal, and the middle 95% of scores are between 72 and 84. What are the mean and, it should say, standard deviation of this distribution? So let's draw a picture and label what we know. It says approximately normal. And typically we would just jump right in there and we put the mean. Well, we don't know that. And we would label 1, 2, and 3 standard deviations above and below the mean, but we don't know the standard deviation. So it feels like we're stuck until we read further. The middle 95% of scores are between 72 and 84. You should know exactly where to put your 72 and 84. Where are you putting those numbers? Where does 72 and 84 go? Yes. 2 standard deviations below the mean. Common sense says the 72, the smaller number goes there. And 2 standard deviations above the mean is 84. Because the empirical rule says the middle 95% of scores are within 2 standard deviations of the mean. Now the rest of it's kind of logic, and there are lots of different ways to get this answer. I want you to take a second and see if you can figure out the mean and the standard deviation. And I don't care how you do it, but I'm thinking of quiz questions and test questions that will be like this. And give you a little information, and then you have to use it to figure out the other stuff. What are you getting for the mean? 78. Some of you found you subtracted and divided by 2 and it was 6, and so you added 6 and you got 78. Some of you just knew, oh, the middle is the average. I'm just going to add them together and divide by 2. Cool. 78. Now, a lot of people will make this mistake. Then they'll tell me that the standard deviation is 6 because they'll just look at these two numbers and subtract them. But those are 2 standard deviations away from each other. So what is 1 standard deviation? 3. Awesome, guys. And we should probably go ahead and put, well, these are test grades, so there's not units on there. You don't have to put like centimeters. Awesome. Okay. This is going to lead me into the rest of the notes today. Let me hit, I know, let me press pause. Somebody answer the door. I want to know this. Could I take this information, this distribution of test scores, and figure out or calculate the percent of scores above an 80? An 80 is not one of those tick marks that we have labeled. So will the empirical rule help us? It actually won't. We could loosely approximate, but we need to be more accurate than that, okay? So if you're asked about a value that is not 1, 2, or 3 standard deviations from the mean, then you need some further knowledge. So stay with me, turn the page. This is going to be just like what I asked you about on the previous page. Here's the 12-year-old boy heights again. $158, $167, $176, $140, $131, and $122. I don't know why I always go out to the left before I go to the left. I've always done that. That's just how my brain works. It says what percent, so be sure you answer as a percent, of 12-year-old males are less than 160 centimeters tall. 160 is right here. Which way would I shade for less than? Okay. Our empirical rule is not going to help us. Now, I can estimate. I do know that my answer should be well over 50%, right? You can see that that shaded region is more than half. Well, before technology was a thing, people would, and some AP Stat students still choose to use something called a z-table. And if you want to use the z-table, I can show you how to do that. But regardless of what your preference is, you have to know about something called the standard normal distribution. So we'll address this problem in just a second. We haven't answered it yet. There's something called the standard normal distribution. And it's going to be your friend because no matter what, if you take a distribution and you standardize everything, and we touched on this in the last set of notes, the mean is always 0, and the standard deviation is always 1 on a standard normal distribution. Back in the day, we would have to take stuff, and we'd have to essentially convert it or standardize it to see where it was on the standard normal curve. So I want us to do that right now. It's a skill that you need, and I want to make sure you know what I'm saying. I'm going to take this 160 centimeters, and I'm going to standardize it. And I'm going to show that work down here. Standardizing is the same thing as finding a z-score. Do you remember the formula for that? What is it? 2 things on top. Divided by mean. Standard deviation, yes, or SD, or sigma, whatever your preference. So the value in this problem that we care about is 160 centimeters. The mean in this problem that we care about is 149. And the standard deviation in this problem that we care about is 9. I'm standardizing. I'm seeing where that 160 centimeter tall boy is on a standard normal curve. Turns out you get 1.22. Draw where that is on the standard normal curve. Do you see anything interesting there? It's the exact same proportion of the area that's shaded. It's identical. It's exactly 160 is 1.22 standard deviations above the mean. You guys, that's what Z represents, is how many standard deviations above or below the mean we are. So these say the same thing. Well, why would we go this extra mile if the calculator can just work in these units? And here is why. Back in the day, or you may choose to do this, you're going to be provided with a Z-table on the AP exam. And if you know that you're looking for a Z-score of 1.22 and you want to find the area to the left of that, this is really cool. You've got this column of Z's, and for 1.22, you're going to go down to 1.2, and across the top you have your hundredths. So if I figure out where this row and this column intersect, that's 1.22, and here's the answer. That shaded region is about 88.88%. So using a Z-table is not hard, I promise. Z-table, 88.88%. Let me show you how your calculator can do this, okay? On a free response question, you would need to draw the picture, you would need to shade it, you would need to tell the AP grader that I'm doing this on the calculator. Normal CDF, open parentheses. Let me show you how to get there. Hit second bars. Second bars. Normal CDF is the second option. Go to that. Look what the calculator needs from you. It needs the lower boundary of your shaded area, the upper boundary of your shaded area, the mean, and the standard deviation. Well, if I just want to stick with these numbers, that's fine. We don't have to go down to the normal stuff, the standardized stuff. Up here, this is going to be really crazy for some of you, but remember how I told you that this keeps going and going and going and going off to the left? So because that shaded region continues out there into space, we're going to actually say that the lower boundary is -1,000. Some textbooks will even say -10,000 because we just want to be safe that we're capturing the data. Somebody let Peyton back in, please. I know, right? It doesn't really have a lot of meaning in this context, but -1,000. What is the upper boundary or the right edge of your shaded region? Why did we draw that stick there? What number is that? That's the 160, yeah. The mean height of 12-year-old boys is 149 and the standard deviation is 9. Enter, enter, enter. It's really close to what the Z-table said. It's 88.92%. But this is how you have to write it. Those of you that want to pass the AP exam, watch, and then I'll answer your questions. You have to tell the AP grader that for lower, I typed in -1,000, comma. For upper, I typed in 160, comma. For the mean, I typed in 149, comma. And for for sigma, I typed in 9. You have to write it like this. You have to have the parentheses. You have to have the word lower, upper, mu, sigma. You have to have the numbers. You are showing what you entered in the calculator for each part, and then you can finally write a sentence answer. About 88.92, always go to hundredths, when in doubt, if you can, percent of 12-year-old boys are, I'm just going to say shorter than 160 centimeters tall. Or you could use your standardized, watch how I do this, you could use your standardized values down here. My lower is -1,000, my upper was that z-score of 1.22, mu is 0, sigma is 1, and there's just a tiny little bit of discrepancy there, but you're still going to get, and the AP grader is not going to say this one's right and this one's wrong. They're close enough. Especially if you're writing down your key sequences in the calculator, you can justify your answer. So it doesn't matter. You can choose. And I know you're probably thinking, why in the world would I do this extra work if I don't have to? And that's a great question. All right, let's do C. Z-table. On the Z-table, the percentage to the area of the left of a z-score of a standardized score of 1.22 is about 88.88%. That'd be your full sentence. Right. Okay, what percent of 12-year-old males are greater than 145? I'm going to make you draw a picture just because I'm mean like that. Get your picture drawn while I help people. You were probably on a different menu item. Keep trucking along, 8th period, if you think you know what you're doing. Greater than 145 centimeters tall. So I'm starting at 145. The empirical rule cannot help me. Greater than means to the right, taller than that. I need to tell the AP grader I'm going to go to the calculator and I'm going to type in normal CDF. My lower is going to be what? Is it -1,000 because that's what we did last time? Or, yeah, look at your picture. It's the whole point of drawing it out. Is the left edge, the lower edge, is that 145. The upper is 1,000. Very good. Positive 1,000. Mu is still the same that it has been. So is sigma. Second bar is normal CDF. Do your thing. And most of your calculator apps on your phone that are emulating this calculator will do this stuff. It might just have a slightly different way that you enter it in. Did you get 67.16? Okay. I like for us to write our sentences in our notes because we're learning how to structure our words instead of just writing down the numeric answer that we typically do in math class. Of 12-year-old males are taller than 145 centimeters. If I wanted absolutely full credit for this, I would probably need to title my graph. And then it looks beautiful. Now my favorite kind are these. Let's save a little bit of time and not draw a picture. What percentage of 12-year-old males are between 140 and 160? So these are my favorite, you guys, because what's the lower going to be? Whatever the lower number is. Because we're sandwiched in between 140 and 160, then that means my lower is 140 and my upper is 160. You don't have to worry about which way you shade. You don't have to worry about negative 1,000 or positive 1,000. But because you have to draw a picture anyway, you would know this stuff. Let's see what percentage of boys are in that region of height. 140, 160, 73.05. What if it said proportion? How would you give your answer? Because I kind of hate that none of these say that, and I want you to get used to that. Mark that out, put proportion. I want to make sure you're comfortable with giving the proportion answer, because it feels awkward to write. You're going to write the same exact sentence, I promise. But you're just going to write about 0.73 of 12-year-old males are between 140 and 160 centimeters tall. Writing the proportion doesn't feel as smooth as a percentage because we wouldn't say that in real life. About 0.73. But we're talking about proportion out of one whole. Yes. Yes. So you have to see what they want your answer in the form of. The AP grader is going to know that that's mathematically the same, but they're going to ding you if it asks for a proportion and you give a percentage. Or they ask for a percentage and you give a proportion. Yes. I don't know exactly what they're going to have. They're going to have a rubric for that. Partially correct, essentially correct, and then it's going to be up to them. So I can't tell you exactly. Oh my gosh, no. Okay, what could we possibly learn next? Well, we're going to learn how to go backwards. The very last thing I need to show you is how to go backwards. Before you turn the page, listen really closely. On the problems that we just learned, they gave you a number on the axis. They gave you the height of a boy. They were asking you to find a percentage. When we turn the page, they're going to do the opposite. They're going to give you a percentage in the shaded region. You have to find the number or the height of the boy on the axis. It's another calculator thing. But you're going to have to know on your quiz on Friday or a test where they're all mixed together, you're going to have to know when to do what in the calculator. So turn the page, I'm going to show you. All of a sudden, it asks us something completely different. It says, what is the 85th percentile of heights? So pause. Let's reverse back to the last lesson. What does being at the 85th percentile of height mean about your height in relation to all the other heights? You're pretty tall. You're taller than 85% of other boys your age. Okay, so it's really giving you a percentage. Because 85% of heights are less than, really the or equal to is kind of arbitrary in this case, but are less than this mystery height. We don't know. We're trying to find that height. So if they give you a percentage and want you to find a number on the axis, you're going to do something different. Let's draw a picture really quickly. I'm proud of you guys for hanging in there today. and tell that you're learning from this. Now, I don't exactly know where to draw my line because I don't know what number height it goes with, but the empirical rule kind of helps me out, and if I lose you here, it's okay. But I just need to kind of, I'm going to say it's somewhere over here. And if you're like, how did she know to draw it between the 158 and the 167? I honestly use the empirical rule, but I don't really have time right now to show you that. It doesn't matter if you end up drawing it in the wrong spot anyway. Okay? But I knew that 85% is a lot, so I'm somewhere over here, somewhere. I just need to know where. What it did tell me is that this less than area, the area to the left, is 85%. Just in case we need this skill in the future, which we will. What percent is in the unshaded region? Okay, keep that in mind. Sometimes it'll give you one side but want you to find the other. Okay, now, we're going to use something in the calculator called inverse norm. That's when they give you a percentage and want you to find the value. Let's see what it needs from us on the calculator so we know what this inverse norm stuff is about. Hit second bars, the same place you find normal CDF, but go down to inverse norm. Here's what it needs. It needs an area, it needs mu, and it needs the standard deviation. What does it mean by area? Well, explicitly on the TI-84s that we use in class, area must be the area to the left of the value of interest. The newer calculators have an updated feature that might let you do the area to the right, but you have to enter in the area to the left on these yellow TI-84s or any calculator like them. So this one's really easy, and you might be wondering why I'm stressing that, because this is just the 0.85. Oh, and enter as a proportion. So don't type in 85, type in 0.85. Area to the left of my value of interest is 0.85. The mean is 149 centimeters. The standard deviation is 9. Here's our answer. The 85th percentile of height for 12-year-old boys or 12-year-old males is about 158.33 centimeters. Calculator saves our butt. What you would have to do on a z-table, this is where it gets tedious, is you would have to take the guts of this z-table and you would have to find the closest number to 85%. There it is in all of those numbers. And then you would have to see that it aligns with 1.04. And then you'd have to take that z-score of 1.04 and you'd have to unstandardize it. Oh my gosh. Why would we do that when we can just use inverse norm? Okay. I want to ask you on this next one, is this a normal CDF or an inverse norm problem? And when in doubt, use the process of elimination. Did they give you the height of a boy? In a roundabout way, they gave you a percentage. Quartile 1 is at the 25th percentile. We're tying together all of our old knowledge. For the sake of time, let's not draw a picture. We know that we're going to use inverse norm. Here's how you would put it in the calculator, or put it on your free response. Tell your grader that the area to the left of the value of interest is 0.25, mu is 149, and sigma is 9. And we find out that the value of Q1 for heights of 12-year-old males is at about 142.93 centimeters. I'm at least going to check with with a picture that I drew earlier of this distribution of heights. Look at the guy who's 142 centimeters tall, and that's going to be a reasonable estimate for quartile 1, 25% overweight. Okay, the last one's kind of challenging, so try and stick with me. Finally, we get a break from 12-year-old boys, and we look at 13-year-old boys. I know, right? The mean height for them is 155. Puberty. The other information that's given is 31% are taller than this value of 160, and it also tells you that it's approximately normal. What's the standard deviation? Let's draw what we know. We know the average is 155. We also know that the top 31% are above 160. I don't really know where that 160 is, but I know it's bigger than 155, so I'm going to go for it. We get so stuck on calculator stuff, so let me just pretend I'm a student. I'm trying to figure out, is this normal CDF or inverse norm? What do you think? Normal CDF? Okay, so if I go to that screen, I could do my lower and my upper, but Andrew's on the right track here. I get stuck right here. That's what the question's asking me. Oh, so it must be inverse norm. Oh, it also is going to, dang it. I guess we just need to put cannot do. No. Is there a different calculator? No. Is there a specific type of normal curve that we know the mean and standard deviation of? Yeah, our friend, the standard normal curve. Ooh. Okay, so how do we use that? What's going on? Like, now what? Okay, let's standardize 160. We're just taking a shot in the dark here. Standardize 160. So I need to find why am I stuck? Okay. We do?
We have the standard deviation for the elsewhere one. So I feel like there's some way that we can put them together.
Do you remember earlier when, do you remember how I showed you this whole thing where both of these were the exact same? Okay, so here they're going to be the exact same, and just because I know the answer, it should be a little bit this way. Okay. So I apologize, it should be a little bit closer to 155. It's okay, it's okay. That's only because I have insight into what the answer is. But I'm cheating. You don't have to know that. Now, Is this still 31%?
Yes.
Ooh, now we might be on to something. Do I know the mean and standard deviation of this?
What about this other thing?
What could I put in the calculator now? Uh-huh. Why isn't the area just 0.31? I made you write it out at the top. You must put the area to the left. Everybody's favorite number, 69. 0.69. I mean, I've taught math for a long time. I know about 69 and 420. And I usually avoid them at all costs. But today I thought, what the heck. All right. What did I just find? Because we're on the right track. What did I just find? Oh my gosh. We just found out how many standard deviations from the mean this is. 0.496. In other words, we just found the z-score. Because by definition, that's what z-score is how many standard deviations you are from the mean. So guess what? Algebraically now, we have everything we need to solve for the standard deviation. So these areas are the same area, so I just use this mean and standard deviation to figure out that it's 0.496 standard deviations above the mean. So I cheated a little bit when I moved it over between 0 and 1, but that's okay. All right, algebraically, because I would hate for this to be where all of you brilliant minds get lost, what would I do first?
Multiple standard deviation.
Yes. What does move back over the thing mean?
Divide by.
Oh.
Move the z-score to underneath.
Move it to under the thing. That means divide by. Yes, it totally is. 5 divided by 0.0 or 0.496. Or you could even copy and paste the answer from up there so we don't round in the middle of the problem. And what do we get? Like 10.08-ish? If we're being extra accurate, I think that's the one. Does anybody need me to show you that? So, the standard deviation of height for 13-year-old boys, yeah, is about 10.08. Oh, you're going to get dinged if you don't put it in context with units. What are the units? Centimeters. I wish all my classes could answer out loud the way you guys do. It makes it so much more interesting. No, I'm dead serious.